So where we left off yesterday is we were graphing the graph with the dot points. And the question asked is a smooth curve where I connected those dots make sense in the terms of this problem situation. So what you got to do is you got to think, can I have a half a day that I am going to look at in this scenario? Would it make sense? Because it tells us that the number is going to double by the end of the day. Do we know it's at the halfway point of the day or any other point like that? And since we do not, it doesn't make sense. We can't count the half part of the days. Plus, we can't have a partial person. A person is a person is a person. So it does not make sense. And that's because when we're looking at this, we need to have only integer values. We can't have negative numbers in this scenario. So we want to describe this pattern as linear, exponential, quadratic, and then write the corresponding equation, which we've already written the equation. The equation was that we had 3 times 2 to the n minus 1. But if we were actually to graph this, we'd need to have it as y equals 3 times 2 to the x minus 1. So this is just so we can get it in our graphing calculator. Then write the corresponding equation. That's what this is. But was this linear, exponential, or quadratic? Was I increasing by the same number each time, like adding 5? Was I multiplying by the same number each time, like multiplying by 2? Or if I take it 2 steps out, is it going to be the same number? So is it going to be increasing on the difference by the same amount? And that's quadratic. In this case, we were talking about increasing by doubling each time, and so therefore it makes this exponential. And this is an exponential equation because the x is in the exponent component. And so let's look at the graph. Okay, so let's look at the key features of this graph. First off, we're not going to be looking at the whole graph because we're only concerned with the positive number. So anything that's happening over here is really not a concern because those are negative values. So let's focus in, and even if we were looking at those, would this ever cross the x-axis? Is there a way for me to end up with a 0 here? Well, no matter how small I get my x, it will never become negative. And so I'll never cross the x-axis. So there is no x-intercept. Because there's no situation where 0 people, after the time that they have uncovered it, knew. Because they started off at 3 people uncovering it, right? So day 1 was 3 people. Now, contextually in this graph, if you look, we can go back and we can see the x-intercept, or the y-intercept. And when we're looking at it, we see that it is touching here at the y-intercept of 0, 1.5. So on day 0, before the election happened, did 1.5 people know the results? No. It doesn't make sense in our problem scenario. So we really can't even consider the day 0 as a part of it, because those are before the scenario started. Now, let's look at how many days will it take before 500 new seniors learn about the election results. And so we can look and see, and I'm pulling my graph over so we can all look at the graph. And I just use Desmos. I'm trying to see when it hits 500. Let me change the settings and we'll just do the Y value going from 0 to, let's just do 600 so we have some room above. And we don't need our X's going that far. Let's say 15 and 0. So we're wanting to see when we hit that 500 mark. And if you look down here, I'm going to go ahead and snip this so we can see it, and I can write on it. So at this 500 point, I am after the 8, and if you're looking down here, it's counting by halves, so here's 9. So I'm between 8 and 9 days. So it's going to take 9 days before 500 will know, because we can't say when in that time frame that 9th person found out. So we said it is between 8 and 9, so that means that there is, after 9 days, 500 seniors will know. And if you plug in that 9, you'll see that it comes up with you can plug it in and find out how many seniors there was. I can't remember what number it was that actually had it on 9 days. So let's look at the next one. Determine the number of seniors that hear the election results on the 12th day. Does the answer make sense in your context of your problem? So let's look at it. Let's use our calculator. 3 times 2 to the 11th. And that gives us 6,144 seniors would find out that day. At this point, and definitely at our school, but at most schools, there won't be that many seniors left to find out at in that situation. And so on the 12th day, when we do 12 minus 1, we get that 11. And we type in our calculator, we come up with 6,144. And this does not make sense because there's not going to be 6,000 new seniors to find out. Ours would have stopped a lot sooner if we were just looking at it for our school. So this is an example of a quadratic pattern. So let's now look at the example of the last one. So I'll give a hint. This is going to be your that was your example of your exponential. Now let's look at your quadratic. And so remember, we looked at this earlier. I kind of did the design, number, and the tiles. So at design 1, we had 5 tiles. Design 2, we have 10. Design 3, we had 17. Design 4, we had 26. So each of these, this was 5. This next one was 7. This next one was 9. So you see how if we go out 2 steps, then we'll end up with the same number repeated. That's what makes this a quadratic, is you take 2 steps out at finding the separation. If this one works, it's linear. If this one works, it's quadratic. If we go further, it will be higher up powers. So Maureen and Matthew both looked at this pattern and they represented it in two different ways. And so let's look at how Maureen did. I want you to spend some time, I want you to think about it. She said n plus 2, you're going to square it and take out 2 of the n plus 1s. I want you to pause a minute and I want you to think about how does that connect into here. So like here, that's saying she took n, so this one was 1, n plus 2 would be that 3 distance, and she squared it. So that's getting that area for that shape. And then she took out 2 of the n plus 1. So this space right here is n plus 1. 1 plus 1. Let's look at this next one. To complete this, then you see how you have a 4 by 4, and this is 2 plus 1 here, and 2 plus 1. And so what she was doing is she was seeing the top of the square was n plus 2, the side of the square was n plus 2, and she's trying to remove these two tiles. That's tiles. And so that's where this expression comes from. Matthew came up with another expression. He said we're going to square and we're going to add 2n plus 2. And let's use technology to help us check check to see if these are equivalent expressions. So my two equations was 2n plus 2 squared minus 2n plus 1 and n squared plus 2n plus 2. So get a graphing calculator of some sort. I really don't care which type, if you want to use your Desmos calculator or if you want to use your Inspire calculator on this. I'm going to use the Desmos one. And so Maureen said, and we can't use n here, we have to use x plus 2, and we're going to square that. And we're going to subtract away 2 of those n plus 1s. And let's go ahead and graph that. And so I have got my graph zoomed in to where we're seeing only the right-hand side. But if we kind of look out farther, we can actually see it is a quadratic. It has that U shape to it. But for our story context, we don't need anything that's negative in either the x's or the y's. So I just kind of zoomed in to that section. Well, let's look at what Matthew's was. Let's type it in. Oops, that's not supposed to be in. There we go, that looks a lot better. And let's type in Matthew's, which was x squared plus 2n, or 2x, excuse me, plus 2. And now you can see that these are overlapping lines. They are the exact same spot. So these are equivalent equations. This is using technology to verify the equivalence of the two expressions. We graphed them both in the calculator or in Desmos and have verified that these are same. So when we look at this graph, we're restricted really just to the positive quadrant 1 because everything else is not going to make sense. We're not going to have negative number of tiles. We're not going to have negative number of designs. So we're restricted to that first quadrant. So only quadrant 1, which is that positive quadrant. Now it says to verify the two expressions algebraically. So we need to see if I was to multiply Maureen's out, will it give me Matthew's? And so remember when we squared something yesterday, that's when we took the box with the n And we're looking at just this section here first. Plus 2n plus 2. And I'm going to multiply it in. N times n is n squared. N times 2 is 2n. N times 2 is 2n. Giving me 4 here. I'm going to do 2 times 2. Which when I combine like terms gives me n squared plus 4n plus 4. Okay? And so that's going to replace this front portion. And so let's go ahead and fill in the rest. So for Maureen, n squared plus 4n plus 4. And then she had minus 2 times n minus 1, or n plus 1. So I need to distribute that negative 2 to both pieces. And so we have n squared plus 4n plus 4. Negative 2 times n is negative 2n. Negative 2 times 1 is a minus 2. And when we combine like terms, we end up with Maureen having n squared plus 4 minus 2 is 2n. 4 minus 2 is 2. So they do match mathematically. Oops, plus 2 there. So to accommodate the outdoor furniture, the grill and the shed and the patio must have an area of at least 125 feet, not including the walkways. So that's not including this space here or this space here. And so really what he's saying is he needs to have plus 2 to that. So 127. And so we need to figure out where, if we look at our chart, and we're going to come back and pull up our Desmos chart, and see when is 127 happening. And so the easiest way to do that is do y equals 127. And we want to find out where that intersection point is. Well, that looks like, if we look at it, it's going to be at 10.225. We can't have a partial design, so he's going to have to go all the way to the 11th design. So let me write this down. And he's going to worry about it at that 1:11:145. Now remember that included the 2 spaces for the walkway. So he's going to have to go out to design 11, which would be 145 minus a 2 for the walkway, 143 tiles, to give him enough room. And since he has to go out far enough to get to where he has it, he's going to need to go out to that 11th spot. And so I want you to look at the design on page 13 and see if you can answer the questions on 13. Or not 13, on the, on the next page on the activity.